So I am Charlene Sylvester, and today I am here with my co-principal investigator, Dr. Justin Schaller. We are going to just provide a short status update related to a New Start project. This was a New Start in fiscal year 23 to develop the next generation US Inlets Atlas and the tools for developing detailed assessments of inlet geomorphology. Our agenda, here today, Justin and I are going to be tag teaming this talk, but we had hoped to introduce our project team, which I'll do next, and then Justin will take over kind of providing the motivation for this work, which was largely driven by needs communicated directly from the field. Justin will also go over we're doing with this New Start. And then I will take the reins sort of back over to go through some of our development efforts this past year related to DEM compilations and workflows related to approaches for doing DEM sort of segmentation. And then Justin will step in to discuss the work that he's been leading with conformal mapping to kind of look at bed form migration or sort of the evolution of the geomorphology features that we're extracting. And then we will both wrap up the discussion to chat through some anticipated products from this work, both short term and looking longer term, hopefully. So the project PDT, again, was formed just about a year ago. So March of 2023, again, Justin and I Matthias Bose, who's on the call today, and he is an ORISE fellow that is also supporting this work. Again, our project funding comes from Dr. Beck with the Coastal Inlets Research Program. And then the district PDTs members are from Mobile District, New York District, and Jacksonville District. These districts are not surprised. Some of our initial sort of pilot sites where we're looking at developing this work are in those districts directly. So we're really thrilled that they've been able to participate in our PDT. And then finally, we have additional sort of advisors, if you will, within ERDIC that are leads for some key products coming out of the Regional Sediment Management Program. That would be Sean McGill for the Sediment Budget Analysis System, and then Dr. Michael Hartman for the core shoaling analysis tool, which is actually comes from the CIRP program itself. Those two specific tools have some direct tie-ins to the work that Dr. Schaller and I are leading. So with that, I think we'll kick over to Justin. Thank you.
Thanks, Charlene, for kicking us off. So yeah, as Charlene said, I'm going to be sort of setting up the why and the what of this, right? So I'll discuss a little bit our motivation and in particular call we had right as this project started. So almost a year ago now in March 2023, we met with that PDT that Charlene mentioned, and those folks are sort of a cross-section of engineers, geospatial folks, and project managers at those districts. And one of the things we did was sort of across and around the inlet. And related to that is another idea of better tracking historical inlet geomorphic change, because that can inform how engineering interventions could further alter sediment transport and morphology, right? So basically using the past to inform the present, which as geologists, we were thrilled to hear they were interested in. The other is a point that was raised to sort of optimize and even reduce sometimes the need for modeling, narrow the focus of modeling by using these GIS tools first. And then there are two sort of additional interrelated questions that they brought up. One is sandy material consistently at one spot? And in thinking about that, particularly in your flood and ebb shoals, if those are used as borrow areas, what are the recharge rates of those sandy spots? And the reasons for those questions range from sort of regulatory to more engineering focused, right? From regulatory perspective, thinking about what are areas of more or less active deposition versus quiescence, for example, and how that relates to habitat. But then in terms of being able to mine out of a particular area with minimal morphological impacts and sort of maximum benefits to a sediment budget. And so in discussing those needs, we also discussed with them what would be a preferred format to receive these types of data that could support these questions. And they said that they don't really want a static map or a report, right? They don't want something that sits on a shelf. They want something that's a little more dynamic, has the potential to be updated more often. And that in general, they prefer sort of a ready-made product that's just shipped and sort of set to go. But in order to sort of limit the additional analyses that they might need to do, but of course they want access to these workflows that we might develop as well. And so it's sort of a yes and approach in that we want to create data products for them, but also give them the tools to create additional products themselves. And so with that in mind, we started thinking, how does this relate to what the current US Inlets Atlas is? And how does this relate to prior work that's been done? And so if you will, Charlene, thank you. So the current US Inlets Atlas, I checked this QR code does still work. It provides a search. It'll get you there. This is also up on the CIRP webpage. But the current US Inlets Atlas is a web map, and it shows a smattering of inlets all around across the US, right? The attribute table that pops up. And in that table is a treasure trove of information, including whether or not that inlet is federally maintained. Are there jetties? If so, what's the offset of those jetties? What's the tidal prism? And then it also links to, for example, some literature that supports those numbers that are in the attribute table, but then kind of gives you a launching off point for learning more about a particular inlet that you might be asked to complete a project on. And then some prior work has set out to expand that current atlas. And with that, thank you, Charlene. So, for example, Tanya Beck and Dave Arnold published a tech note in 2019 that outlined an effort to expand the content of the US Inlets Atlas for 20 different inlets on the west coast of Florida. And derive an estimate of the volume of the inlet's ebb tidal delta shoals. And to do this, they cast these parallel lines along the coast outside of the influence of the inlet, and then interpolate sort of that space in between. So you end up with this sort of surface of what the coast would probably look like without an inlet, and then you know the real bathymetry as well, and so you can back calculate a volume of those. And for each of those 20 inlets, the current atlas also has the newest, sort of freshest National Coastal Mapping Program LiDAR bathymetry data populated there as well. And then I'll highlight one more prior work effort on the next slide. And this was done by someone that a lot of us, I think, virtually or in the real room there at CEB know well, Lodorai, who was an intern for CEB for quite a while. She developed two different additional sort of workflows, one of which was done as a pilot study and one of which was documented as a ArcPro toolbox and Jupyter Notebook. So the first was a tidal basin hypsometry pilot study. So the example on the right of the screen is from Shinnecock Inlet. And so for that, sort of that top panel there, she grabbed the continually updated shoreline product from NOAA, as well as the bathymetry for the back barrier environment of that inlet. And then was able to sort of develop these simple classes of elevation ranges within the back barrier environment in order to get at a hypsometry curve, which is the final product that you see at the bottom. And so that hypsometry curve plots, in the case of an inlet, depth, as well as the cumulative percentage of area that falls within that depth range. And this comes from river basin research, right? So normally you would plot elevation and cumulative percent area of the river basin. But here it's telling you a lot about the morphology of the back barrier environment. So for example, what you see is that obviously close to the inlet throat, you've got these sort of deeper depths that dominate. But then as you get into your back barrier environment of marshes and tidal flats and shallow bays, that bathymetry rapidly shallows, and that's what dominates the largest percentage area of a particular inlet. And so this is a product that could be expanded throughout the atlas. And then the other is that she developed a tool for better characterizing the cross-sectional area of an inlet. As we all know probably pretty well, it can be hard to nail down one ideal cross-sectional area, right? If you're looking at a textbook, an inlet has this perfect cross-sectional area shape, and from that we can calculate tidal prism really accurately. In reality, obviously, that's not always the case. And so Lodorai standardized a workflow for capturing inlet cross-sectional area and better calculating or estimating tidal prism. And so in reviewing all these needs from the field and reviewing the past work that's been done with the US Tidal Inlets Atlas, now we can look forward to what the next generation of the tool can look like. And for that, I pass it back over to Charlene.
Thanks, Justin, for that nice summary of the prior work towards Tidal Inlets Atlas and sort of for the vision for the next generation US tidal inlet. That enables better calculations of sediment volumes that are so critical to our sediment budget development. Ideally, would leverage existing tools to automate any workflows that would result in the development of these standard data products that could then sort of feed that one-stop shop or the next generation tidal inlet atlas. We do believe that these standard products, it's pretty critical that they are effectively ready for the next step, whether that's integrating the volumes with ongoing initiatives with the sediment budget analysis system, and or are available for use to maybe interpret or better understand results coming from efforts such as the core shoaling analysis tool. And then the Inlet Atlas itself should be expandable and readily able to integrate any new data sets that become available. And hopefully at the same time, there's the opportunity to also ingest all the work that's been done for the current version of the Inlets Atlas. So that work would be migrated over to this next generation Inlet Atlas as well, so that those efforts are still available for use and informing our understanding moving forward. So we've been talking about this first year we have been kind of working on piloting these workflows for a number of inlets in Mobile District, Jacksonville District, and New York District. Hence the PDT members. Those pilot inlet sites are listed or shown on the slide here in Figure A. And so for all of those inlets, we have been doing some data compilation, which I'll address in just a minute, and DEM development that can be used to run the workflow. We are looking at basically 3 different workflows that we have tested so far at East Pass Inlet. They're located in Destin. These workflows include, that I'll be talking about, are the relative relief workflow, as well as another workflow with geomorphons. And those 2 workflows are actually, very similar and aimed at sort of segmenting the DEMs themselves. And then Justin, again, will be kind of jumping back in to talk about some of the conformal mapping work that he is leading with Katie McFerrin. So addressing the DEM component, of this, for any of these inlets, the first step is to conduct a thorough inventory of data that might be available for these inlets. Based on prior experience, past, projects, we like to look at NOAA's Digital Coasts Data Access Viewer for identifying data sets that might be available to support, this work. And when we do that for Destin, there are a number of data sets that are actually, available. So we will go through and download whatever data sets are available. The nice part about the Digital Coast application is that we can download the data in a product that is effectively ready for analysis. So to support this work, we do have a preference to have the data in the UTM projection in meters, as well as the vertical datum being specified as NAVD 88 and also meters. And so what we actually look at from sort of those data requests is an actual digital elevation model product, which you're seeing there, for example, the 2018 Corps of Engineers National Coastal Mapping Program post-Michael survey. That being said, some of these individual data sets coming from programs like the National Coastal Mapping Program may have gaps or data voids in the bathymetry due to a number of reasons. And for that, we want to look for other sources of data that might be useful for filling these data gaps. So you will usually look towards the Corps of Engineers hydrographic survey data that's provided through the eHydro program. So here we have the eHydro viewer, where you can kind of do that same sort of data inventorying, and find a survey that might be temporally, I guess, consistent or close to another National Coastal Mapping Program survey, for example. Those surveys can all be downloaded. There's a number of products, that are available, but it's important to note that a lot of the data products from eHydro are not in a datum or projection that's compatible, with our sort of preferred datum and projection. So we do have a workflow that Rakia Williams has been helping us with to take the sort of hydrographic survey soundings and convert those into depths in UTM meters horizontally, and then NAVD 88 vertically. So this brings sort of 2 different data sets to the same datum, which means then that they can be merged, which you're seeing in the graphic on the far right side of the screen, and I'm calling that an eHydro-filled digital elevation model. This is an example here at a 3-meter resolution, and that's important. So certainly some of the topo-bathy LiDAR data sets that we're using are certainly higher, resolution than that. However, some of the eHydro data sets are not. So that 3 meters was kind of the happy compromise between the 2. Once those data sets are merged, there could still potentially be data voids in the DEM. And so here on the left-hand side, we are showing the result of a void filling technique that utilizes an inverse distance weighted interpolation to fill any voids in the DEM. And we do employ sort of a maximum distance, that can be looked at for using points in the interpolation, and also a sort of a max void size that we would, be willing to fill. And then finally, we employ some masking of the DEM to remove the portion on land, the topography, right? Because again, we're interested in inlets here. And then we are also doing some masking of just kind of to remove any sort of extra interpolated areas. So we, remove any interpolation artifacts. So that results in sort of a topobathy masked final DEM. I have examples of the DEMs that we've constructed for East Pass Inlet shown here for 2015, 2016, 2018, and 2020. These are all displayed kind of using the same color scale, where these are elevations, again, reference to NAVD 88 in meters. And of course, we can readily identify some changes in that ebb tidal shoal. These DEMs are ideal for analyzing kind of in a spatiotemporal way. We can leverage existing tools in the ArcGIS Pro software to compile these DEMs into mosaic data sets, which from there we can then create a multi-dimensional, or what Esri calls a multi-dimensional data set that enables the development of some quick sort of summary statistical products, kind of looking at the entire DEM, I guess, spatial extent, but through time. And so here on this slide, I'm just showing this change in elevation over time for 4 different points noted by those colored dots that you see on the screen. That yellow dot there from the center, of the navigation channel, for example, shows a general trend where elevations, are sort of decreasing, or we are shoaling in that very basic kind of sense. And then here, again, we're showing sort of just a statistical mean surface. So that's just the average of all the elevations from 2015, through 2020. And similarly, on the bottom, there is just kind of an elevation range statistical, surface. And then, with that, you can readily see the areas of the tidal shoal and inlet geomorphology that are changing. One thing specifically we've been looking at are what we call anomalies. And shoaling compared, I guess, to the mean surface. And likewise, the red colors would indicate deepening compared to that mean surface. And again, that's per kind of time slice, if you will. So for 2015, 2016, 2018, and 2020. And I think you'll see, in Justin's conformal mapping approach that these statistical surfaces, are pretty important. And I think, there's lots of insights that we can glean from them. And with, adding additional data sets, whether they be data sets, in the future, or even more historic, data sets that are represented here, sort of the more time slices that we can add to this multidimensional data set, the better our understanding of the systems at play here, the physical processes could be achieved. So that leads us into workflows to compute what we call a relative relief. Again, this is just an approach to be able to assess a DEM and sort of, for each elevation, in the DEM, just basically drawing a comparison to between that elevation and all of the elevation adjacent, to it. So for example, for each of like the squares that you see here, we would kind of look at those 8 neighbors and say that the square in the central is either like higher or lower than the surrounding elevations. And that enables us to differentiate different geomorphology features that might be present in the DEM. We do that at both fine scale and broad scale. So here I'm showing what I call a fine scale. At the broad scale, this would be a 90-meter fish net. And these are scale dependent approaches. And I think we'll see later that you need that sort of fine scale to be able to assess or extract your kind of fine scale geomorphic features, whereas you might want like a really broad scale if you're trying to, I guess, get after a really, say, large shoal feature, for example. So with these fish nets, again, we compute a series of zonal statistics. So for each of these squares, we're calculating a maximum value, a minimum value, a range, a mean, standard deviation, etc. And then with those zonal statistics, we can construct surfaces that are needed to compute the relative relief. Here I'm just showing sort of the minimum surface that's constructed, again, using inverse distance weighted interpolation. And where that comes in is the actual calculation of relative relief, which was provided in the paper by Wernet et al. In 2016, where you effectively, for each elevation in the DEM, you subtract that sort of minimum surface, from your fish net, and then you divide it by kind of the range that's represented by your max and your min surface. And then the results of that are shown here for kind of that 30-meter like fine scale and then the 90-meter broad scale. And the values do scale between 0 and 1. So the sort of the white areas or the values closer to 1 would be indicative of any kind of concave geomorphic features in the landscape. So for example, the edge of the ebb tidal shoal is readily apparent. And then a values kind of closer to 0 would be indicative of more like convex or like pits and valleys in your geomorphology. And again, comparing the fine scale to the broad scale, you can really see where some of, say, the finer sand waves in the inlet itself are kind of getting muted out at the broad scale. So hence that's why there's the need or the desire, I should say, for both this kind of fine scale and broad scale assessment. That leads into the geomorphons, which is yet another DEM segmentation approach that is also scale dependent. This is work that is in the paper by Jasowicz and Stefanski in 2013. What they call geomorphons. Those are provided there in slide C. And so looking at kind of that fine scale, and again, the broad scale, we're seeing effectively a DEM like classification image with the different geomorphons associated with the colors that you see here. But again, it's a way to sort of identify or highlight features that you might be interested in extracting. This was just implemented with the Geomorphons Landforms tool in ArcGIS Pro. This is a relatively new tool for ArcGIS Pro. This workflow had previously been implemented in GRASS GIS. There are a number of parameters that you do need to specify for running this. I've listed the parameters here that we've used for East Pass, but it should be noted that as we implement this workflow at other inlets, I think these parameters will be different. But I think we can show that at least for a given inlet, the parameters are consistent and generally applicable. So I think a future next generation Inlets Atlas should also retain kind of the parameter sets that we're using to run these tools. That would be good to have handy. And so to kind of summarize our relative relief, geomorphons work, I think we've shown that at a spatio-temporally kind of rich, inlet, we have opportunities to identify the regions of the Ebb-Shoal navigation channel, that are changing. We are well aware that not every inlet has as nice data as we have at East Pass. There are definitely data limitations. So our next, I guess, case study is going up north to Fire Island Inlet. And there, I think we have a few options, where we do find data limitations that will at least allow us to populate the US Next Generation Inlets Atlas. And then, as I mentioned earlier, our ORISE fellow, Mateus, will be implementing these workflows at the pilot inlets that we identified. And here we're showing an image provided by Mateus, kind of just that anomaly surface product for Wilderness Inlet near Fire Island. With that, I wanted to kick the discussion over to Justin to continue our discussion on workflows.
Thanks, and a reminder to folks to please, of course, feel free to jump in with questions. Been thinking about over the last year is conformal mapping. And what is conformal mapping? Well, in terms of applying conformal mapping workflow to inlets, I think the really gold standard approach was outlined by Stuart Pearson and others in a 2022 geomorphology paper. And in that, they established a workflow and essentially new or pretty novel methods for mapping inlet bathymetric change. And there's three parts to this. The first part is something similar to what Charlene was showing with those multi-dimensional data sets, where you have these surfaces in XY coordinates, right? So in the cases that Charlene was showing, UTM coordinates, right? And here what you're seeing is mean bathymetry, and in the middle minimum bathymetry, and then on the right maximum bathymetry for Ameland Inlet in the Netherlands. So this is the work from Pearson and others. And they have a equally rich, if not richer, data set spanning sort of 1975 to 2021 for this inlet. Multiple sources of bathymetry, but regardless, numerous bathymetric surfaces. And what they can do is, once they have those means, the minimums, the maxes, they can, next slide, please, Charlene. Thank you. They can calculate an envelope of bathymetric change. So that's on the left side of the screen, and that's just your maximum minus your minimum. A surface anomaly for each year. So for example, 2021 was the most recent data for Ameland Inlet. And so that's 2021 minus the mean in that case, as well as an active delta thickness. So that particular year, 2021, minus the minimum in that case. And as you sort of stare at these for a minute, you start to see the beauty of capturing inlet geomorphic change in this way, because you immediately start to see areas of relatively active deposition and relative quiescence across the inlet. Then go to the next slide, sort of the next part of this effort that Pearson led was to look at surfaces in polar coordinates. So instead of XY coordinates, you could actually use polar coordinates. And what that does is that aligns your bed elevations and your geomorphic change with sort of the dominant transport directions across most inlets. So it doesn't matter if you're going east to west, north to south, but you're picking a center point in the inlet, and then you've got polar coordinates through it. So what you see on the right is at the top, you've got your XY space for both 1975, so that's the one slightly more to the left, and then on the further right is 2021. You've got XY space with a polar grid shown, and below that, you go ahead and bend your mind a little bit, and you're in polar space now, where rho is on your y-axis, and that's just your distance sort of across the inlet, if you will, right? And then so north to south in this case, and then you've got your theta, your actual polar position sort of along shore on the inlet. So that's just bed elevation. But on the next slide, here's where I think the magic starts to happen, where you can track a volume anomaly in this polar space as well. And so again, sort of similar orientation at the top. He's got an XY space still, but with the polar coordinate shown on it. And then beneath that, you're actually in that polar space. And it starts to look like a piece of modern art, but when you sort of pull one of those strips out, and that's what those two boxes are on the left, you end up with a temporal plot of your theta and a temporal plot of your rho, your sort of cross shore and your long shore. And there you can track these changes in volume anomaly through time, and you're actually getting a landform change in the inlet. So your bars moving and migrating, your shoals forming, all of that. Okay, so that's what Stuart Pearson did. On the next slide, I'll tell you, or start to tell you what, oh, I forgot. There's a third step to this whole process. I got ahead of myself. The third thing in this conformal mapping idea is that at least when you have these rich data sets, you could start to do a cell-by-cell calculation, right? So you can break your map up into these individual cells and compare elevation differences at sequential time steps. And so is there change from one time step to another? Yes, no, and if yes, then label it with that new time step, and you iterate through all of your data sets. And what you end up with is a map of the chronostratigraphy. So the age of a particular deposit. When did that sand grain or piece of mud fall out of suspension and end up where it was? And so in mapping that, you can, again, see where fresher deposition has occurred in the inlet versus areas that are more quiescent. Okay, so now I'm caught back up with myself here. We can talk about some of the benefits of this work as well as some of the limitations, and then what we actually did this year related to all of this. So I've highlighted some of these benefits, right? You're aligning your grid with the primary sediment transport pathways. You can see these stable and less stable regions, and you can get at the ages of deposits. One of the limitations, though, is that right now this code to do this work is not accessible. We've met with Dr. Pearson and had like a really nice conversation. He outlined some of the MATLAB workflow, but this is not up, like, for example, out on GitHub or anything yet. So our goal this year was simply to replicate the workflow, and then in the future make it more accessible for the districts. Maybe that's initially a Jupyter notebook, but maybe ideally long-term some sort of ArcGIS toolbox, as well as sort of standardized products that end up on the US Inlets Atlas. So for the year one efforts, Katie McFerrin has recently stepped in to help with her MATLAB knowledge, as well as her inlet geomorphology knowledge. And we've been able to start replicating this workflow. And so on the next slide, we'll see what Katie has been able to do. So she's replicated the step one, right, where you've got the mean bathymetry, the minimum bathymetry, the maximum bathymetry. And we can see a lot of deposition occurring and a lot of activity occurring both in sort of the dredged channel as well as the outer ebb shoal bar. And as the next step, what Katie's been working on is to now move into that polar space. And so at the top, just like Pearson, she's got the XY space, but with the polar grid sort of shown overlaying on it. And then she's also then moved into polar space. And now you can see that bathymetry sort of warp around and plot onto that polar plot. And then now she's actively working on the volume anomaly part of this. And throughout, what she's been doing is just really good documentation of that workflow and good management of that script as well, so that we can share it out. This with the relative relief and geomorphons work, in that, you know, we need to move on to a case study site that's a little more data limited. So we'll be doing the same work at Fire Island as well. And when we showed our project development team the Pearson paper, some of their takeaways were related to how great this would be for beneficial use and strategic placement, because you can better nail down sediment pathways, at least when you have good multiple data sets. And that things like the active delta thickness would be really great for targeted dredging or mining to figure out, you know, where can you maximize speeding up natural bypassing to benefit a downdrift beach, for example. And then in terms of environmental studies, understanding areas of active deposition, perhaps where you've got critters living that are more adapted to sort of disturbance anyways. And then identify areas of shoaling, right? So shoaling hotspots. And for next steps, we'll also be passing this work on to Mateus, and he's likewise already started running with this. And so you see, for example, an envelope of bathy change at Wilderness Inlet, again, near Fire Island, New York. And that work from him already highlights, you know, for example, your greatest bathy change is occurring right in the inlet throat as that thing closed, and as well as offshore once you're able to resume sort of sediment transport along the coast as that inlet closed. So some really exciting work coming out of this, thanks to Katie and Mateus. But that's the conformal mapping workflow.
So here is where we had hoped to wrap up our discussion on talking about some anticipated products. I'll how a district user might use those services in the ArcGIS Pro environment. That is our enterprise, GIS application in the Corps of Engineers. And then we have a few examples as well as how you could extract these products programmatically using the REST API from a Jupyter Notebook, for example. The products will also allow us to develop sort of the prototype of this next generation Inlets Atlas, and start to develop the geodatabase feature classes that we'll need for kind of housing results of all this analysis. And then finally, we are working on getting a tech note submitted that is summarizing the progress that we've made in this last year. And then Justin, you want to address the longer term?
Sounds great. Thanks, Charlene. Yeah, so over the long term, we would love to be able to present this research at ASBPA or a similar conference. And then thankfully, getting us all the way to August, Mateus will be NORISE fellow, right, for that sort of 7-month period. And we've already been in discussions with Mateus that he would love to sort of incorporate some of this into one of his dissertation publications. So this will probably end up being one of his primary chapters. So that'll be a really nice product from this work as well. And then in out years, we would love to go from that demo image service to sort of a full-blown web service with data. So a true next iteration of the US Inlets Atlas, and associated with that, some ArcGIS tools where folks could create their own additional products as desired. And with that, we want to thank you for your time and attention, and we're really happy to take questions, comments, anything of the sort.